Okay. So today we're talking about probability. We're not talking about functional analysis. So back on. So probability is really the foundation of statistics. Like, if I know none of you guys are math majors, but once you get to upper level, you take a whole class in probability before you do statistics, which is what I did last semester. Now I'm taking statistics. Probability is the basis of statistics. Statistics is applied probability. The reason that it's only chapter 12 is because, since this is an intro course, we want to set you guys up with the more practical things and some of the mechanics of it, just to ease you guys into this. But from now on, like, you're going to realize that probability has underlied everything we've done so far. The normal model, for example, is a probability distribution. Chapter 15 talks about what a probability distribution is. So you're going to notice when we do like the complement rule, you guys have already been using that. A few definitions. So let's talk about an event. An event is just a collection of outcomes. And an outcome could be something like, if you flip a coin, heads or tails is your outcome. An event is kind of using what we talked about the first week. It is a set of outcomes. It's just a bunch of outcomes written together. The sample space, which we'll usually call capital S, is the collection. It's the collection of all events. So there is an event would be like, if you flipped a coin 10 times, you might get like head, tail, whatever. The sample space would be an infinite length of heads and tails. That's one way to think of it. There is sample size is an important thing. We were talking about that a bit last week. I'll go over our quizzes at the end of the class, but remember how we had the first question about the precision of the sample size, right? And it was like 100, what's more precise? A sample of 100 out of 1,000 people, or a sample of 200 out of 10,000 people? You guys remember that? Almost everyone got it wrong. It was not 100 out of 1,000. It was 200 out of 10,000. Not because it was a percentage. The population size does not matter at all. It's just the bigger the sample size, the better. And there's a thing that tells us exactly how big that sample size needs to be, which is the law of large numbers. Sorry, this new pen kind of like makes me write like a calligrapher. I don't know why. Basically, the long run relative frequency of an event's outcome, sorry, approaches the true relative frequency. In essence, your sample probability is going to approach the population probability in terms of like using the language of sample and population things. So like, for example, if you flip a coin 10 times and you get 6 heads, that's a sample probability of getting heads, bless you, of 0.6, right? And we all know a coin is 50-50. But let's say you flip a coin, instead of 10 times, you flip it 1,000 times and you get 498 heads. Now you're, that's 0.498. That's almost 0.5. You guys see what I mean? As your sample size increases, you're going to get closer to the true probability. I just gave it to the math office. Yeah. Now, in general, your sample size has to be at least 30 in real life. You want your sample size to be at least 30. If I like usually when I gave you guys like quiz statistics and stuff, it'd be a skewed distribution. In essence, you're gonna have a unimodal and symmetric histogram, and the probability is gonna be close if your sample size is at least 30. That's what it means. Any questions? Oh yeah.
For all cases.
Kind of. That's just a number that statisticians agreed upon. There's some proof for it. I don't remember, but 30 is just like the rule of thumb. Did he talk about sampling distributions yet? I don't remember. Has that term came up yet? I don't think it does until chapter 15. Basically, there's a thing called sampling distribution, which is if you just keep taking more and more samples, and it's called the central limit theorem. If you take samples of increasing size, you're gonna get eventually like a perfect normal distribution. And the mean of that normal distribution is gonna be your population probability. So, and at least 30, sample size at least 30 is like what we need at the minimum to at least be like kind of good. So like, there's 20 something people in this class. It's not enough. Like if I showed you histograms for this class, they're all skewed because the sample size is too small. But if you like took all the test grades from the first test, which is like 200 people, it'd be like a very nice unimodal symmetric histogram because that's just how it works. Okay. Probability. You guys have all heard the term probability. It is a number between, 0 and 1 or 0 and 100%. That is the likelihood of an event. The probability of getting a head on a random coin toss is 50%. Getting a 1 on a dice is 1/6. You guys have all heard these things in real life before. There's two different types of general probability. There's empirical probability. Empirical, which comes from the long run relative frequency. Long run means after you sample it a bunch of times. If it's a real world thing like the stock market, right? You don't really want to look at a stock or like a mutual fund after a month. You want to look at it after like 5 years because you need time. So like an empirical probability would be like the probability of getting a heads is 50%. These are like things that we've observed over time that we basically consider true. All the general probabilities that you've heard of are empirical probabilities. Or that's not true. Empirical is if you observe it. Like if you flip a coin 10,000 times, you get 5,000 heads, that's 50. Theoretical is like the theoretical probability. I mean, there's not much of a definition there. Or based on a model. We will be talking about probability models in chapter 15. Binomial, geometric. The normal model, which we've talked about before, is a probability model. Yeah. So based on a model, just some equation or whatever. Okay, now we're going to talk about the probability rules. There are 5 rules. I'm going to combine the chapter 12 and 13 rules into one thing because they're pretty similar. The first 2 are all the same. Rule 1. Let's just say A is an event. Then the probability of any event is between 0 and 1. So if you get a negative probability, if you get a probability bigger than 1 or bigger than 100%, you've made a mistake. Like you're 100% wrong. So that's always like a way to check yourself if you're doing a problem. A probability is always between 0 and 1 of any event. 2, the probability of the sample space is always 1. The probability of everything is 1, the highest number possible. 3. The probability of A complement, which if you guys remember is the probability of not A, is 1 minus the probability of A. Remember when we did the normal distribution and we talked about the probability, the area above a number is 1 minus the area below? That was the complement rule because it abides by probability. So these are the same for both chapters. Now we're going to go on a little side tangent before I tell you 4. Generally, when we have events, you might have something like this, right? Here, there is A and B. But what if we have something that looks like this? This whole thing is S. Does anyone know what the term is for when A and B are not touching? I mentioned this in like the first week. Yeah. Yeah, these are disjoint events. A synonym for that is mutually exclusive. You should definitely know both. And what this means in the real world is these are two events that cannot possibly happen at the same time. Like the probability of you being here and the probability of you taking a nap is 0 because you can't, well, that's actually not the best example. The probability of you being here and the probability of you going to a party right now is 0, you know? You can't be in 2 places at the same time. So they're disjoint events. That means that the probability of A and B is 0. So there's 2 versions of 4, which this is the addition rule. Knowing the names isn't that important, but there's the disjoint case, which is probability of A or B is probability of A plus probability of B. And then there's the non-disjoint case, which is the more common case. Probability of A or B is equal to probability of A plus probability of B minus probability of A and B. Notice that since we said right here probability of A and B is 0, it is still over here. It's just minus 0, so we don't write it. And here's the reason for this. In this picture up here, right? Everyone looking at that top one? The intersect part, the middle part, right? We're counting it twice when we do probability A and probability B. We're counting that twice. So we have to subtract it once. So we only count it once. Does everyone see that? See, because if I colored it in, like, we count it once, and then we count it again, but we only want to count it 1 time. So we have to subtract it once. So the one on the right is the general case. 5, the multiplication rule. This has 2 cases for independent and dependent events. So independent events are 2 things that don't rely on each other. Like the probability of you guys getting dinner tonight and the probability of you coming to class theoretically are independent. You know, you'll be, you eat dinner after class instead of during class, right? They shouldn't rely on each other. In that case, the probability of A and B is the probability of A times the probability of B. We'll be using this rule a lot implicitly, especially it was used a lot in your homework. The dependent case, like the example I used in office hours was if the event A is the probability of you guys going off campus to get ice cream tonight, and the probability, and B is you guys having a car, right? You probably won't want to leave campus if you don't have a car. So those 2 events are not independent. You guys see what I mean? Like intuitively, like they're not separate. There is a reliance of one on the other. before I define that, well, actually, I'll just write it. The probability of A and B is the probability of A given B times the probability of B. It is A vertical bar B. That bar is the word given. This term right here is called conditional probability. And it's going to come up a lot because in real life, conditional probabilities are easier to find than probability of A or probability of B, even though it doesn't seem like it. Like every time we do, let's say, a medical study, right? When the probability of getting cured from the vaccine, right, is the probability of getting cured given you got the vaccine. So it is a conditional probability. Then statisticians use these rules to find the probability of A and probability of B separately. So conditional probabilities are what you get from doing experiments. I want you guys to notice something. This term and this term are the same, and this term and this term are the same. So an event A is independent if probability of A equals probability of A given B. Similarly, you can reverse the numbers. So probability of B is if probability of B is equal to probability of B given A, they are independent. You can also check if they're independent using the independent formula. Probability of A and B is probability of A times probability of B. Any of these three equations, depending on the context, can be used to check if an event is independent. And it's really important in real life to know if two events are independent. Because, obviously when we give you examples in class, intuitively you can kind of figure out if something's independent or not, but in a lot of real world scenarios, we don't know if like two, proteins are independent or whatever, or two, different meteorological events are independent. So we use probability to find out, and that's very important for the real world. This conditional probability, the formula for it, notice how you can, if you divide by probability of B on both sides, you get the formula. This is the formula for conditional probability. So that example of getting ice cream and having a car, it would be the probability of getting ice cream given having a car. When you have conditional probability, it implies there's an order to it. One event has to happen first. Specifically, B, the thing on the right, has to happen before A. You need to have a car in order to go drive and get ice cream. You need to get a vaccine shot in order to have a chance of being cured. You guys see what I mean? So the event B is what chronologically will happen first. Any questions so far? Okay. This is just a lot of the probability rules. At the end of the day, we got to do some problems to show you how these work. Okay. So these are, you have your 5 rules, which there are some different versions. In both cases, the version on the right is the general version. Independent, generally this bottom equation is the most common way probability A and B equals probability A times probability of B. That's the most common way we check. So the reason the first two work is that if the probability of A is equal to the probability of A given B, that means A doesn't depend on B, right? If the probability of you guys eating dinner tonight is equal to the probability of you guys eating dinner given you come to this class, means that being here does not affect your ability or desire to eat dinner. Like that's what it means intuitively, which again could be important if we want to know if two events are independent or dependent. I want to go through some of the homework questions because that's the best way to do this stuff. First, I'm going to talk about chapter 12, number 9. And again, if anyone has any specific ones they want me to go over, let me know as we go on. If you didn't do the homework, I definitely recommend going through it. It's just good practice at the end of the day. You know, the next test is coming up, especially if you have time over break. The more practice problems you guys do, the better you'll do in this class. Like that's just always how it works for any class that really involves problems, you know, which is the case for most STEM type classes. So for each of the following events, we're going to list the sample space and tell whether we think the events are equally likely. So the first is going to be toss 2 coins. So we usually use the set bracket notation, which on a keyboard is like shift and the brackets. So all I just got to do is think about it. First time I get a head, then I flip it again, another one. Then I get a head and then a tail, then a head, tail, then a tail. Those are the 4 possibilities. Do you guys think these are all equally likely? What do you think? Yes or no? Raise your hands if you think yes, they're equally likely. Yeah, they are equally likely because each of them are probability 1/2 times 1/2. We're using the independent multiplication rule because two coins, 2 dice, 2 whatever are always going to be independent like that. If they're separate, you know, every roll of a dice, especially if they're different dice, are always going to be independent. So each event is equally likely. The next is number of having a number of boys in a family of 3 children. So you can have 0 boys, 1, 2, or 3. In this case, they would not be equally likely. Just using the probability rules, like this and this would have a probability 1/8, I believe, and they're not equally likely. Then it's flipping a coin until we either get 1 head or 3 tails. So first time we get a head, we're done. The next time we get a tail, then we get a head, done. Tail, tail, head, tail, tail, tail. Those are our 4 options. These are also not equally likely. This has probability 1/2, this is probability 1/4, and these both have 1/8. And then part D, roll 2 dice, record the larger number. So that's just gonna be 1, 2, 3, 4, 5, 6. Right? Those are the only possible options. But they're not equally likely because we're rolling 2 dice and choosing the higher number. You know, for 3, dice 1 is a 3, dice 2 can be a 1 or a 2 or a 3. For 4, 1 dice is a 4, the other is a 1 or a 2 or a 3 or 4. They're not equally likely again. Any questions on this one? This is important just because at the end of the day, when we're deducing, like theoretically, we're deducing probabilities from looking at the sample space of events. So in these scenarios, these are the only possible outcomes. Obviously, they could just happen multiple times, but these are the only unique outcomes. Did anyone do specific questions in chapter 12 that they want me to talk about before I continue? I have a few more, but all right. Yeah. About lights. Yeah. Okay. Yeah. So I'll just read to you guys. It's a pretty short problem. You purchase a 5-pack of new light bulbs that were recalled because 6% of the lights did not work. What is the probability that at least one of your lights is defective? Okay. This, what I'm about to say, is a very important identity and probability. This will 100% come up. I mean, this is going to come up at 10 more times just in the problems we're about to do. It's going to be on your test. It's going to be in your final. This is a general rule. If you need to know that the probability of some event is at least 1, this is equal to 1 minus the probability that x is 0. In English, the chance that you have at least one thing is the complement of having nothing, right? Doesn't that make sense if you say it out loud? The opposite of having at least one thing is having nothing. Anytime you see at least one thing, you're immediately going to this formula because you will see it. Like just in office hours, it showed up at 10 times. It'll be on your test. It'll be in your final. So, you know, star this in your notes, put it on your flashcard, whatever. So in this case, we purchased a 5-pack of light bulbs that were recalled because 6% did not work. I'm going to say probability of work complement is 0.06. So the probability that at least one did not work is equal to the probability that none don't work or all of them work. So one thing we have to do is assume each light bulb is independent. You don't have to write this on your test or anything. I just want to do it for completion. Because otherwise you can't really do this problem. So the probability of a light bulb working is 1 minus 0.06 is 0.94. Right? Everyone with me so far? So this is probability of a light bulb working, probability of a light bulb working 6 times, which is 1 minus 0.94 to the 6th power, because you're multiplying together 6 times. Whatever that number is should be your answer. Someone will just have to plug that into a calculator. Any questions on how I set that up? Yeah.
1 6 power.
Because there's, oh, wait, sorry. There's 5 light bulbs. 5. Yep, sorry about that. Can someone plug that into a calculator, please? Yeah, always have, from now on, like, I need some people to always have calculators out because I can't do this in my head. .733. Oh, so it's 1 minus that? Gotcha. Double check that that's the right answer. Should be. Yep. But it has as 0.266 or whatever. We can just do 0.267. In general with this stuff, a good rule of thumb is like 3 decimal points, unless like the 3rd decimal point is 0, then it doesn't matter. But in general, 2 to 3 decimal points is good. Any other questions on this one? It's an important example as well. Okay, so I'm going to talk about number 51 now. Same chapter. On 9/11/2002, the New York State Lottery number came up 9/11. What is the probability that the winning 3 numbers match the date? So we have 911. For each number, there's a 1 in 10 chance of getting that number, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Each number is independent. So it's 1/10 times 1/10 times 1/10, which is 1/1000. That would be part A. So the probability that the winning numbers match the date is 1 in 1,000. Part B, what is the probability that a whole year passes without this happening? So the probability of, I don't know, no matches. So this would be, well, this would be the probability of matching. So this is 1 minus 1/1000, which is 0.99, well, it's 0.999 or it's 999/1000. Everyone with me so far? Yeah. Well, actually, one thing I should note about this is if it is for part A, if it is a date in October through December, you know, like Halloween is like 10/31, which is a 4-digit number. So it's a 1/1000 chance if you're between January 1st and September 30th. But essentially 1/1000 for the first 9 months of the year. Part C. Oh, wait, I didn't finish this. So the probability of no matches is this to roughly the 300th power, because there's about, well, it's more like 365 minus the amount of days in the last 3 months. You'll get roughly the same answer. But that's because for roughly 300 days in the year, this equation works and you don't want it to hit any of these days. And this gives you around 0.741. Does this make sense? Any questions on this? Again, this is all just us using the multiplication rule a bunch of times. The probability that January 1st doesn't match 1/01, that January 2nd doesn't match 1/02, and so on for the first 9 months of the year. That's what this probability is. Okay. Part C, probability that the date and winning lottery number match at least once during any year. So the probability of at least one match. As you can see, this would be 1 minus the probability of no matches. Now, part 2 was the probability of no matches. So it's 1 minus 0.741, which is 0.259. Everyone good so far? Part D. If every one of the 50 states has the same lottery system, what is the probability that at least one of them will come up 911 on September 11th? So this is the probability that at least one state matches. Which is 1 minus the probability of no state matches. Which is going to be the probability that doesn't match in one state is 999 out of 1,000. And there's 50 states. So it's to the 50th power. And then the answer is 0.049. Everyone good with this question? Anyone need me to say anything again? This all making sense? Starting to make sense? How we're applying these rules? In a sense, in this question only used the complement rule and the independent multiplication rule. We haven't used or the addition rule or disjoint event, whatever. Everyone good so far? Okay. I want to do one more from chapter 12. Just because at the end of the day, the more practice with this stuff, the better. 45. It's about bowling. A bowler can bowl a strike 70% of the time. One thing to do, whenever you read a question, immediately write down the information you know. I'll say probability of strike is 0.7. Right? You have, at the very least, you write this down, you know, it's 1 point on a test, right? Versus 0. Just from taking information from the question, putting it, showing us that you're interpreting the question correctly, at least. Assume each bowl, each frame is independent. What is the probability that she goes 3 frames without a strike? So probability of no strikes in 3 frames. Well, probability of strike complement or no strike is 0.3, right? So this is going to be 0.3 times 0.3 times 0.3, which is 0.027 or 0.3 to the third. No strike times no strike times no strike. B. Makes her first strike in the 3rd frame. So that is no strike times no strike times strike, which is 0.3 times 0.3 times 0.7, which is 0.063. Everyone good so far? Okay. Next part. Has at least 1 strike in the first 3 frames. Of course, we're using our rule, 1 minus the probability of no strikes. We already did the probability of no strikes in part 2. So that's 1 minus 0.027. That's 0.973. And then finally, bowls a perfect game. So probability of 12 strikes. Well, that's 0.7 to the 12. That is 0.014. Any questions about this one? How's everyone feeling about this stuff so far? Is this all starting to make sense to you guys? Just want to make sure, because this is, you know, don't hesitate to ask questions, because this stuff is going to be throughout everything else we do in the rest of the class. So it's better you guys make mistakes now and let me know so we can fix them now. Especially since there's no quiz and no graded homework, which I guess a lot of people didn't do because it wasn't graded. But definitely do take time over break to do some of these problems. And I guess you'll probably have homework for next week, so take time to do some of these too. Chapter 13, it's going to be a lot of similar stuff, but there's slight variations that I really want to talk about, like more word problems. So we're going to do chapter 13, number 23, which is interpreting probabilities from a contingency table. This is blood pressure. This is cholesterol. So we have a relative frequency table. They just put the percentages as decimals. The first part is, well, I'm going to call cholesterol, well, C and BP. So the probability of high cholesterol and high blood pressure. What do you guys think? How would we get that information from this table? It is one of the numbers on this table. Yeah. Yeah, it is this number. It is 0.11. So any of the numbers in this table are something and something. They are always the multiplied probabilities. This is part A. High blood pressure and high cholesterol. Part B, what is the probability of high blood pressure? So for this, you want to add up these two numbers. 0.27. Any questions? So. Okay, the next part is very important. What is the probability that a man with high blood pressure has high cholesterol? A man with high blood pressure has high cholesterol. Can someone tell me what they think that is in the symbols in the probability notation? I already told you what it is. Can't answer. Someone give it a shot. Yeah. For part C? Yeah, well, I was asking the notation first. You skip to the answer. So, a man, that is right, but a man with high blood pressure has high cholesterol. Let me ask you a question. Which one is coming first? High blood pressure or high cholesterol? Or are they not? Are they simultaneous or are they happening in an order? Yeah. Other way around. It is high cholesterol given high blood pressure. A man with high blood pressure, he has high blood pressure. Given that he has high blood pressure, what's the probability he has high cholesterol? You guys see that? Because this is very subtle and it's, again, it's really easy to just reverse the order or not recognize it's conditional. A few key words. If you see the word given, that's a given. If it is known, with blank has blank, something that implies an order. Any of these things give you a hint that it's conditional probability. A man with high blood pressure, so that's your second thing, has high blood pressure, has high cholesterol. So cholesterol given high blood pressure. Oops. So this is the probability of high blood pressure and high cholesterol over the probability of high blood pressure. Well, these are the two numbers from the previous two parts. It's 0.11 over 0.27. This number is 0.407. Everyone good with that? Okay. Part D. A man with high blood pressure, well, the probability that a man has high blood pressure if it is known that he has high cholesterol. So someone tell me what to write in these parentheses. A man has high blood pressure if it is known that he has high cholesterol. Yeah. Yep, it's the reverse. So the numerator is the same. It doesn't matter which thing you write first, and when you write probability of A and B, you could do B and A, same thing. It's the denominator that changes. So this requires you to find the probability of high cholesterol. And it is adding up this row. So it's 0.11 plus 0.21, that's 0.32. And that is 0.344. How's everyone feeling? This is the majority of probability calculations. I have a question for you. I think this was also on your homework. Are high cholesterol and high blood pressure independent? All the numbers you need are on the page. Someone tell me what I should do. The three numbers you need are all on this page. Which equation do we want to use? Yeah. Mm-hmm. It is either part C or part D. And this makes sense, right? The condition should not matter. So it should be the same thing. The first term should match. Probability A equals probability A given B. Because it shouldn't depend on B. That's the point. Well, this is 0.27. This is 0.344. It's not equal. So the answer is no. And if you want to like write it out, you could say probability of blood pressure is not equal to probability of blood pressure given high blood pressure given high cholesterol. So they are dependent. Yeah. Yes, they will be the exact same number. Yeah. You even if you do the calculation, it'll be the exact same number. Yeah. I mean, the other answer would have been probability of high cholesterol equals probability of high cholesterol given high blood pressure. Also, if you don't like, if you can't think of a good simple notation, you could just write out the whole thing. I'm just trying to shorthand it. Or any of these three would have led you to the same result. Because this is like probability of A equals probability A given B, probability of B equals B given A, and probability of A times probability of B equals probability of A and B. I'm also going to do number 35, and then that might be it. Especially since there's no quiz. So I want you guys to pay attention to how I am writing down the information from the question. Because it's always something that's going to become more important for this class is how you take a word problem and find the important numbers from it. I'm going to read it once first. A survey found that 73% of Americans have a home phone, 83% have a cell phone, 58% of people have both. Immediately, you should be thinking, okay, those are three probabilities. So a survey found that 73% of Americans have a home phone, 83% of Americans have a cell phone, and 58% have both. This is how you write down the information from the question. You know, you could call the variables whatever you want. You could even write out the words home phone and cell phone. That just takes more time. Everyone agree with me so far? Right. If a person has a home phone, what's the probability that they also have a cell phone? Can someone tell me what that is? I'll read it again. If a person has a home phone, what's the probability that they have a cell phone? And right here. What? Now, what's the notation? What I write in here? Don't give me a number. Just tell me what I should write here. What do you think? If a person has a home phone, what's the probability that they also have a cell phone? Other way around. Yeah. If they have it, that's the condition, right? That's the given. So they have a home phone first, then what's the chance they also have a cell phone? So it's cell phone given home phone. Yeah. So it says if a person has a home phone, what's the chance they also have a cell phone? So the home phone is first. They have a home phone, you know. Think of all our parents when cell phones became a thing. Everyone had a home phone, right? And then, you know, Apple comes out, whatever company did it first. Cell phone, whatever. Then the chance they have a cell phone. So the cell phone came second. the chance of them, there's probably a higher chance that they got a cell phone if they had a home phone, that they want to stay connected or whatever. But they had the home phone first, then what's the chance that they also bought a cell phone? Yeah.
So like the thing, like first, like if you have a home phone first, does that always go last?
Yes.
Okay.
The thing that's first is second in the equation. Yeah, because it is cell phone given home phone. Probability of having a cell phone given you already have a home phone.
Okay.
It is probability of getting cured given a vaccine, not the other way around, So this is probability of C and H over probability H. So it's 0.58 over that should be 0.73. I think this is around 0.8 or so. What's the number?
0.79.
Thank you. I was looking at the wrong question. Yeah. Everyone good with that so far? Okay. Next part. Are having a home phone and a cell phone independent events? Someone tell me which equation you want to use. It's really easy to do that multiplication equation because you have the three things you need right there. Which numbers are going on which side of the equal sign? How do you set this up? Someone tell me. Yeah, Gabby.
Probability of C and H. Probability of H.
Now I use this symbol because that's just what I use. I might just do that sometimes. I'll try to use the words, but at least for my classes, we only use those symbols. All right, someone multiply those two numbers on the right side and tell me if that equals 0.58. It's probably not going to, but. What is it, Jamie? Yeah, well, those aren't equal. So they're dependent events, which makes sense, right? Like if you're reclusive and you don't have a home phone, you're not going to buy a cell phone. But if you have a home phone, you're probably more open to upgrading to modern technology, Like logically, it makes sense. You can't use logic in your answer, but the math checks out with real life. That's the point. Part C. Are having a home phone and a cell phone mutually exclusive? Oh, that reminds me of one thing I forgot. Well, let me scroll up. So it's asking, is the probability of A and B 0? Is it? No. Because the probability of C and H is 0.58. So mutually exclusive is the same thing as disjoint. Remember this, put this on your flashcard. Mathematically, the definition is that the probability of A and B equals 0. There's no chance of them happening at the same time. Before I continue, any questions on this example or anything? Okay, I'm about to say is very important. It'll definitely show up on your test, on your final. Independence is not disjoint. Disjoint events can never be independent. Write this down, start in your notes, put it on your flashcard. Independent events can never be disjoint. So if you have a picture that looks like this, A and B are never independent. They are always dependent. They must overlap for there to be a chance of independence. This can be independent. This is always dependent. I will show you why. Let's say probability of A is 0.3 and the probability of B is 0.4. They are disjoint, so the probability of A and B equals 0. So then you check if they're independent by using this formula. You get 0 is equal to 0.12. It's not. The only way this works is if probability of A and or probability of B equals 0, because then you have 0 equals 0. But then what's the point of even doing that? So independent can never be disjoint. You'll 100% see this as, you know, probably like a multiple choice type question or whatever. Easy points. If you just put this on your flashcard and a number. Okay. Any questions about anything we did? Or any there's one more thing I definitely gotta talk about. A tree diagram. Let me think of a good example. A college student has, or let's say 75% of Binghamton students are STEM majors. Out of those who aren't STEM majors, 40% work in technology. Also, 60% of STEM majors work in tech. First of all, there's a lot of things going on here. There's a lot of different probabilities. The way you work with these is by drawing a tree diagram. Which I'll let you guys, can everyone read this? Any wording clarification? All right, so first you start with a point. Then you draw 2 lines. This is going to be 3/4 and this is going to be 1/4. This represents STEM and non-STEM. Then from here, 60% of STEM majors work in tech. So, or let's call this S or S complement. Then you have tech, or no, tech and tech complement. This is 6/10. This is 4/10. This is 4. You know, I'm going to change this. I'm going to change this to 30% work in technology. 30% and 70%. This would be the tree diagram. For this. Have any questions on how I drew this? I see it was kind of like it's like a flow chart pretty much with probability. So if I asked you the probability of being a STEM major and working in tech, anyone have any ideas of how you get that number? Something to do with this number and this number. Yeah, you'd multiply them. So it's 3/4 times 6/10. That is 9/20. Well, 9/20. And from here, you can answer a lot of questions really similar, you know, not STEM and tech would be this times this. That's 1/4 times 3/10. It's 3/40 or whatever that is in a calculator, or that's 7.5%, but. And you can do a whole load of these things. You know, if I ask you the probability of STEM major given, or sorry, tech, working in tech given your STEM major, you know, the probability of STEM and tech over probability of tech. We know the top one is 9/20 from above, and we know the probability of, well, okay, actually, this is a harder. Let me take a step back. First of all, I wrote this wrong. The denominator is not the easiest thing to find. It is not apparent what is the probability. What am I talking about? No, I'm thinking something else, sorry. This is 9/20 over 3/4. And whatever that is your answer. The hard one is the other way around. STEM given tech. If you guys did the readings, this is a thing called Bayes formula. I don't fully think you need to know it, but it is important to know. So when you have it like this, we don't know what the probability of technology is. Straight off the bat, there's no one number on here that answers that. The numerator we know, it's 9/20, right? It's the same numerator. But the probability of tech, this is a very important identity. So the probability of tech, in this case, is probability of tech and not STEM plus the probability of tech and STEM. I'll show you this in a picture in a minute. But this is how you would find this number. On last semester's test, there was a question like this and almost everybody got wrong. But this is how you would do that. So, well, we've calculated these two things. It's 9/20 plus 3/40. So whatever that number is your answer. It's 18/40 over 21/40. So that's 18/21. In general, the probability of A is equal to the probability of A and B complement plus the probability of A and B. Please put this in your notes and remember it. This is very important. And I'll show you why. So we have A and B. The probability of A and B complement is just this part, right? And the probability of A and B is the middle part. Well, those two add up to the probability of A. This whole big thing is called Bayes formula. I believe you don't explicitly need to know it, but you also kind of do. Yeah, so you will not be asked to write it down, but you need to know it. But I mean, this is what it is. So, you know, it's a conditional probability, but the denominator is, you have to find it. It's not just given to you. How are you guys feeling about this? Do you want me to do another example or with this type of stuff, or is everyone thinking they're okay? Otherwise, we're done. Anything? All good? Okay. All right. Thank you. So